Having discussed the cases of heavy and critical damping, let us now consider light damping. And if you recall from the beginning of the lecture, this is the case when gamma square over 4 is less than omega 0 square. So that lambda 1, which was gamma over 2 minus square root of gamma square over 4 minus omega 0 square, can be written as gamma over 2 minus I omega 1, and lambda 2, which is gamma over 2 plus square root of gamma square over 4 minus omega 0 square, can be written as gamma over 2 plus I omega 1, where omega 1 is equal to square root of omega naught square minus gamma square over 4 less than omega 0. So, the general solution x t, which I have been writing as c e raised to minus lambda 1 t plus d e raised to minus lambda 2 t, is going to be, in this case, x t is equal to e raised to minus gamma over 2 t c e raised to I omega 1 t plus d e raised to minus I omega 1 t, which is equivalent to writing this as e raised to minus gamma over 2 t some amplitude cosine of omega 1 t plus a phase constant phi. This is the general solution in the case of a lightly damped oscillator. It is oscillating with the frequency omega 1, which is less than omega 0, which makes sense because it is being slowed down all the time. So, it takes longer and its motion is decaying. So, a general solution may look something like this. Is the exponential like this. The distance keeps on decreasing with time. Let us analyze this more carefully. So, if I were to write x t is equal to c e raised to minus gamma over 2 t cosine of omega 1 t plus phi, and take the case of where I took this oscillator, stretched it out by a distance, let us say a, and then let go, how would the solution look? So, since x 0 is equal to a, this would be equal to c cosine of phi, and x dot 0 is equal to minus gamma over 2 c cosine of phi minus c sine of phi, and this is equal to 0. This tells me that tangent of phi, or there should be an omega 1 here, tangent of phi would be equal to minus gamma over 2 omega 1, and from that I can also calculate what coefficient c should be, since a is equal to c cosine of phi, c is equal to a secant phi, which is a square root of 1 plus tangent square phi, which will be equal to a, I have already calculated the tangent, plus gamma square over 4 omega 1 square. So, the motion when I take the particle out and leave it is going to look like x t is equal to a, the distance up to which I pulled it out is a, gamma square over 4 omega 1 square e raised to minus gamma over 2 t cosine of omega 1 t plus phi, with tangent phi being minus gamma over 2 omega 1. If I were to plot this, it starts with a distance a here, and the motion goes something like this, because there is a factor of e raised to minus gamma over 2t, multiplying it. So, this is how the motion looks like in lightly damped case. X t equals a square root of 1 plus gamma square over 4 omega 1 square cosine of omega 1 t plus phi, with phi being tangent phi being minus gamma over 4 omega 1. So, slowly the particle starts losing its amplitude. Most of the time when we talk about a lightly damped oscillator, it is the case where we do not want damping to be there. So, we want gamma to be much less than omega 0. In that case, you will see that omega 1, which is equal to omega naught square minus gamma square by 4, is roughly equal to omega 0, and tangent phi that we looked at minus gamma over 2 omega 1 is also roughly equal to 0. So, I can write the general solution as amplitude e raised to minus gamma over 2 t cosine of omega 0 t. Let me call this the case when gamma is much less than omega 0, very lightly damped oscillator. It so happens that in these cases there are two time scales, one related to gamma and one related to omega 0. Therefore, I can talk about averages of the system energy and so on over a few cycles. Let me explain further. If gamma is much less than omega 0, you will see that by the time the solution decays significantly, there have been many oscillations of the system. So, if I observe the system over a short period of time, that time which is much smaller than 1 over gamma, over that I will find that system moves roughly with the same amplitude, and t is much greater than 1 over omega 0. So, within this time there have been many oscillations, but at the same time it is much less than 1 over gamma. So, amplitude has not changed significantly. So, in that case, when I write the solution x t equals a e raised to minus gamma over 2 t cosine of omega 0 t, I can really think of this system having a time dependent amplitude a t and then oscillating with this time dependent amplitude as cosine omega 0 t. And then I can talk about averages over many cycles. Let me explain now. Let us talk about energy. Energy E is 1/2 mx dot square plus 1/2 k x square. In this case, I can roughly write this as 1/2 m d over dt of a e raised to minus gamma over 2 t cosine omega 0 t plus 1/2 k a e raised to minus gamma over 2 t cosine of omega 0 t square. And taking the approximation that gamma is much less than omega 0, you can write this energy as 1/2 k a t square, which is equal to 1/2 k a initial square times e raised to minus gamma t. So, the energy can be written in this form. Let us see how it decays. E t over t, you will see, is E 0 e raised to minus gamma t times minus gamma when I take the derivative. So, this is really as minus gamma E t. In writing this form of the energy, I have neglected gamma square in comparison with omega 0 square. This you should keep in mind. So, the energy really decays as dE dt equals minus gamma, the energy present at that time. Why am I able to talk about energy or amplitude at a given time is precisely what I told you earlier. Because gamma is much less than omega 0, there are two time scales, one related to 1 over gamma and one related to 1 over omega 0. So, within this time there are many oscillations. So, for a short period I can think of this as an oscillator moving with time dependent amplitude. Then I define something called the quality factor for a lightly damped oscillator. As I said earlier, most of the time when I am dealing with lightly damped oscillators, I want the leakage or the decay of energy to be as small as possible. So, quality factor would be high when the energy stored is really large and leakage or dissipation of energy is very low. So, this is defined as energy stored divided by energy dissipated per radian of cycle. Energy stored at any time is E t, and we have seen that dE dt is minus gamma E t, and the time that it takes for it to complete 1 radian is going to be t over 2 pi. So, this comes out to be omega 0 over gamma. I take the magnitudes. So, there is no question of minus sign. This is known as the quality factor of an oscillator. Higher the quality factor, less the decay of energy. So, let us conclude this lecture by saying that we learnt about heavy damping, we learnt about critical damping and understood the difference between critical and heavy damping, and realize how critical damping is important when we want to damp out certain impulses within a very short distance and short time. And then we learnt about lightly damped systems, their average energy and their quality factor. In the next lecture, we are now going to introduce a force that drives the system and see how it responds to that force.